This is the first of two videos on mass spectrometry. Much like I did for IR, this first video is more of an introduction, kind of goes into the theory, and then the second video is going to be more specific examples. So mass spectrometry is primarily used to determine the molar mass of a compound and also helping to determine its formula. What happens in a mass spectrometer is the compound is vaporized and then ionized, and then it breaks up into fragments. And then the masses of the ions of these fragments are then detected and graphed. And so this is a schematic of what goes on in a mass spectrometer. So we start here where our samples get injected into the mass spectrometer. We then heat them up to vaporize them, and then we bombard them typically with electrons. And that tends to ionize or remove electrons from our molecule, and then it breaks up into fragments. And many of those fragments have a positive charge. And things that have a positive charge can be deflected in a magnetic field. So then we take that beam of positive ions of the fragments from our molecule, pass that through a magnetic field, and the different fragments will be deflected by the magnetic field to different degrees. Heavier compounds will be deflected less, or things that have higher charges will be deflected more. And so based on the amount of deflection of the fragments, we can tell what their mass to charge ratio is. And then we detect those fragments coming out of the magnetic field. So the most common way to ionize the molecules is by electron impact, since we have a high energy beam of electrons that we smash into our molecules. And usually that causes an electron to be ejected from the molecule. So we end up with a cation. And sometimes the cation stays together, and so we end up with a cation that essentially has the same mass as our parent molecule because the mass of electron is negligible compared to the masses of nuclei. And so when the radical cation stays together, when it remains intact, that is known as the molecular ion. And it generally has the same mass as the parent ion. Now what usually happens is after ionization, the molecule doesn't stay together. It actually breaks into fragments. It breaks into a radical that is neutral and we can't detect with the mass spectrometer, and then typically also a cation that we can detect. Now, what we measure in a mass spectrometer is not actually the mass, it's actually the mass to charge ratio, or the M to Z ratio. But due to the fact that the charge is usually 1, generally the mass that we detect is the mass of the fragment that we're observing. And so here's an example of what a mass spectrum might look like. And so this is the mass spectrum for methane. And so you can see we have a number of different peaks, and these represent the relative abundance of these fragments that we're detecting. And what we plot down here on the x-axis is the mass to charge ratio. Again, because the charge is usually 1, Z is usually 1, we can often interpret this as being the mass of the fragment. Now, whatever the highest peak in the spectrum is, we call that the base peak. So the base peak is the tallest peak. In methane, the base peak happens to be the parent ion, right? And we can see, right, the mass of methane should be 12 for the carbon, plus 1 for each of the hydrogens, so it should come in about 16, right? And that is what we see for the base peak. Usually we will see a really small peak above the parent ion and the base peak. We'll talk about where that comes from in a later slide. Now, the other peaks that are smaller than the molecular ion represent fragments. So in the case of methane, right, if I pop off 1 hydrogen, I'll get an M to Z ratio of 15, and so that was the peak just below 16, obviously, right? And then the other peaks represent removing more hydrogens. So for methane, we'd expect to see peaks at 12, 13, and 14 for pulling off the other hydrogens. Here's another example of a mass spectrum. This one is for benzene, and for benzene, the molar mass is 6 times 12 is 72 for the carbons, plus 6 times 1 for the hydrogens is 6. So the molecular ion peak for benzene, we would expect to see at 78. And it turns out that for benzene, the peak here at 78, the base peak is also the molecular ion peak. We saw that was true also for methane, but it's not always true. All right, this is the mass spectrum for pentane. And so the molecular ion peak is generally the highest peak, plus we'll have a little one with a mass number of 1 greater than that. And we can see in this case, the molecular ion peak is not the base peak. The base peak is always the tallest peak, and this is the fragment that we observe in the greatest abundance. And so it turns out, right, benzene doesn't fragment easily, but pentane does, and so that's why the base peak is not the molecular ion peak. All right, so very often the first step in analyzing a mass spectrum is to identify the parent ion peak. And the mass to charge of the parent ion is equal to the molar mass of the compound. Now, one thing that's often helpful, generally if we have an odd molecular ion peak, that generally means that there's an odd number of nitrogen atoms in the molecule. If I have an even massed molecular ion peak, that generally indicates that there are no nitrogens, or I have an even numbers of nitrogens present. Now, what about what we call this M+1 peak, right? So here's methane again. This was our molecular ion peak. And then where does this little peak at a mass number of 17 comes from? Turns out that this is a result of the isotopes of carbon. So we know that not all atoms of a particular element have the same number of neutrons. Atoms of the same element that have different numbers of neutrons are called isotopes, and carbon-12 is by far the most common isotope of carbon, but carbon-13 exists, about 1% of all carbon is carbon-13. And so this little M+1 peak is due to the presence of carbon-13. So in carbon-containing compounds, which is almost all organic compounds, right, we'll generally have one small peak, one mass number higher than the molecular ion peak. And I'm actually going to skip this slide. We don't have any specific examples where we're going to have to do these types of calculations. Now, sometimes there is an M+2 peak, and this is also due to isotopic effects. Chlorine has 2 abundant naturally occurring isotopes, chlorine-35, which is about 76% of all chlorine atoms, and chlorine-37, which is about 24% of all chlorine atoms. And so there, in a natural sample of chlorine, there are 3 times as many carbon-35s as there are carbon-37s. So a signature to look out for, to know that we have chlorine in our molecule, if we have an M+2 peak that's about 1/3 the size of the molecular ion peak, that's a dead giveaway that we've probably got chlorine in our compound. Another instance when we have this M+2 peak, right, where we've got another peak 2 above our molecular ion peak, is in the case of bromine. Now, the 2 most abundant naturally occurring isotopes for bromine are bromine-79 and bromine-81. Because their relative abundance is about the same, we would expect that the molecular ion peak and the M+2 peak to be almost the same height. And so when you have this pair of peaks around the molar mass of the compound, or right near the molecular ion peak, that's a dead giveaway that we've got bromine. All right, so after we identify the molecular ion peak and look for, right, if it's odd, that's telling us something about the numbers of nitrogens. If we have an M+2 peak, that's telling us if we have chlorine or bromine. Another thing that we often look at is what are the fragments? And so how does the compound fragment? And so if we consider pentane, so the molecular ion peak for pentane is going to be, right, for carbons, I've got 5 times 6 is 60. And then I have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 for the hydrogens. So the molecular ion peak for pentane is going to occur at a mass to charge ratio of 72. But when we fragment pentane, right, we can typically break it off here, where we're essentially chopping off this methyl group, right? And a methyl group has a mass to charge ratio, or has a mass of 15, right? 12 for the carbon, 3 for the hydrogens. So if I see something, if I see a peak at 15 less than the molecular ion peak, right, that's typical of losing a methyl group, right? An ethyl group has 2 carbons, 24, plus 5 hydrogens, 29. So if I see a peak 29 less than the parent ion peak, right, that's probably a methyl. And we can see the same thing for losing a propyl or losing a butyl group. All right, so here is the mass spectrum of pentane again. So I have the molecular ion peak, and then I have, right, a peak at M minus 15, right? This tells me that I've lost a methyl, and then these other fragments are due to losing various numbers of hydrogens, right? The M minus 29, I've lost an ethyl, plus losing various numbers of hydrogens, right? I've lost a propyl and a butyl. Now, this slide is pretty important, and the reason I want to draw your attention to it is because this goes over some things that we've sort of skipped. So by jumping ahead to chapter 14, we've skipped a discussion of the stability of carbocations that we have in some of the chapters that we'll get to later in the semester. And so when we're analyzing the mass spectrum, not all fragments are equally likely. And when I break up this particular compound, the most likely way that it's going to fragment is by breaking this bond. And so resulting in a propyl coming off and leaving me behind with this particular carbocation. And the reason this is the most likely way that this compound is going to fragment is because of the stability of this particular carbocation. And so the carbon that has the positive charge, we can classify it by how many other carbons it's attached to. And so because this carbon is attached to 3 other carbons, that makes it a tertiary carbocation. And that is the most stable type of carbocation. So the more carbons that are attached to the carbon with the positive charge, the more stable that carbocation is going to be. So a primary carbocation is more stable than primary or secondary carbocations. And so that's why this is the most abundant fragment in the mass spectrum of this compound. And another thing to point out, right, these radicals that come off, their stability is also a factor in the fragments that we see. So you might say, well, why don't we see right, an M minus 15 peak from popping off this methyl? Because that would also result in a tertiary carbocation. And the difference is the radical that comes off, right? So this methyl radical that would result from breaking that bond, right, if I compare that, right, a methyl to a primary radical, right, this is going to be more stable than a methyl, where this carbon that has the unpaired electron isn't attached to any other carbons. So because this methyl radical is less stable than the primary radical from cutting this bond, this makes this the most likely fragmentation that's going to occur. All right, just a couple more slides. Alcohols and amines that we'll see on the next slide behave a little bit differently than just hydrocarbons or things that have halogens. And so the 2 most common things that happen with an alcohol is we have what's called alpha cleavage. So we're breaking the bond essentially that's next to the oxygen-carbon bond. Or we can actually lose a water, and so after it's ionized, we end up popping off an OH and an H, and so we lose a water. And so very often in the case of alcohols, we don't see the molecular ion peak. And instead we see the products that result from this alpha cleavage and from pulling off a water molecule. And I know this may seem a little bit complicated. I have an example of this in the next video where we look at the products that would form from the fragmentation of an alcohol. Okay, and so just like alcohols, These amines often undergo an alpha cleavage, where next to the carbon-nitrogen bond, we often break that. And then carbonyls undergo what's called a McLafferty rearrangement. And so for alcohols, amines, and carbonyl groups, we often don't see the molecular ion peak. In the case of carbonyls, we often see an M minus X peak, where X is some even number. There are no examples in the book of this McLafferty rearrangement, so I wouldn't worry as much about this. And like I said before, I've got an example in the next video on how an alcohol typically fragments. All right, so my last slide on this video just has some typical fragments. Honestly, I don't remember these numbers, right? When I'm looking at the fragments, I can generally just, figure this out myself, right? I know, right, common fragments are going to be a methyl, right? And so a 12 plus 3 is a 15, or an ethyl fragment, I've got 2 carbons, 24 plus 5 hydrogens, that gives me the 29. So, I don't generally try to memorize these numbers. I can generate the numbers if I need them when I'm analyzing a mass spectrum.